I'm Tushar. I'm going to show you how to model soil structure interaction using Abaqus CAE. Here we consider the problem of a pile foundation, and we are going to model a soil medium and a cylindrical pile and a interaction contact interaction between cylindrical pile surface and soil surface, and after that I will be apply some load on top of the pile to see the deformation behavior and state of stress. And since we are modeling soil, so we need to model the self weight of the soil and the corresponding state of stress, because the cell because of in soil there is a significant stresses due to its own weight. So this will be done using so-called geostatic procedure, which allows us to simulate the state of stress in the soil without any significant deformation in it. So let's start. I will start with creating a pile first. We consider a pile of 0.5 meter radius and height of or length of pile is 0.5 meter. I make some mistake. What is the radius? Radius I thought I want it to be 0.1. Okay, done. And after we create this, let's create a few sets which will be useful for many purposes, and another set for the top. Okay, this is positive z axis, so this will be our top. Let's rotate it, right, top. Now a few surface, because this will be needed for defining contacts, right. Another surface for the bottom one, right. And okay, now we have pile. Now let's create another part for the soil using 3D, and for this let's use this one. We're creating and height of the medium to be 1, and we have this. Okay, now we have this solid. Let's create a hole for where the pile will be placed. To do that, we can do that a shape, cut, extrude, and we'll use specify, and this is a surface, and we will use 0 0 0 as a default, and this one. Then let's create the same circle of same radius, same as the pile, so it will be 0.1, and this radius is 0.1. okay, now we are okay, not through all, but we'll go up to halfway. Okay, because we have a pile of length 0.5 meter, right. Okay, so this hole has been created here, right, but for better mesh purpose we should partition the solid. Okay, to do that you need, what we need is a datum plane, and the datum plane location is 0.5 meter from top, and we partition it. Partition cell, use datum plane, and we use this datum plane. Partition done. Now we save it. Okay, now the partitioning is done. Now time for creating few sets. Okay, and for these sides are done, and bottom we need these to apply boundary conditions. Okay, almost all sets. Okay, another set is needed for this inner side. Why? You will see. Okay, we need a few surfaces. We'll name this surface, create this surface similar to the one in file. Okay, so we have this surface bottom and sides. Okay, and these sides for the boundary conditions we will be using. Okay, we have now part module ready. We need to define the material properties. Let's create a few material properties. One for the pile, which will be elastic, and let's consider a few densities. I am using some number. Okay, 100. Okay, these are just some typical number. You should use material properties following some document, like some paper, published document, experimental result. This should be the one we should follow, but I am using just to show, using this number just to show how to create a model for pile foundation. And for soil, okay, for pile I have used basically elastic material properties, and let's use the same density, elastic. Let's use 1. Idea is the elastic Young's modulus of pile material set for concrete should be significantly more than that of the soil, right? And plasticity will use, say, more Coulomb plasticity is more suitable for soil. Okay, friction angle, let's use something like 30 degree or something. Here comes this yield stress. We'll use something like this. Okay, I have tried these numbers before to see which numbers works, because everything should be in a proportionate, otherwise there will be problem, right? So I'm using some proportionate number, which of course, if to be appropriate, we should follow some paper and pick up suitable number which is reasonable for soil and pile material for, say, concrete. Alright, we have material properties. Now let's create a few sections. One will be for the soil, solid section for soil, and another for the pile, solid section for pile. Now time to assign the section. For this bulk soil, we will use the soil. Done. Dismiss. For pile, apply the same, and pile. Okay, now property module is done. We have defined the material properties for both of the parts. Now we go to assembly, where we bring these two parts and assemble them. Okay, now the pile is not in the correct location, correct location. So what we need to do is translate. We are translating the file, and we know how where it should be located, right? Easiest way will be to click somewhere here and drag up to top, but I know the coordinates, so I'll use the coordinates. So starting point is 0 0 0 and end point should be, we are trying to lift it by 0.5 meter vertically upward. Let's see how does this look. Okay, it seems to be correct. It's important to do this done. Okay, as it is assembled, so let's save the model and okay, step model. This is important. Here we'll be defining 3 steps. This initial step is the by default, where the initial conditions or the boundary conditions are defined, like the existing boundary conditions which is present from the beginning of the analysis. We'll create 3 additional load steps. Step 1 will be our geostatic, where we will simulate the self weight of the soil without any significant deformation in the soil. Okay, so nonlinear geometry will not consider material nonlinearity here, and increment size, let's use just in 2 increment. I am trying to finish this load step. Okay, this is geostatic. Now step 2 is will be our contact initiation, where we will introduce the contact between pile and soil and it will be static general type procedure. And let's also finish it in just 4 increments, because total is, these are pseudo time, this is not actual time, just pseudo time, representative time 1 to 5. Okay, and we create another step, final step, to apply some load on top of pile and see what happen, I mean the deformation behavior, state of stress under externally applied loading. And here we should use some smaller increment. We are telling something like in 10 increment we would like to apply the entire load. Alright, so we have created all the load steps. Now time to create the interaction. To create interaction, first of all we need to create a few interaction property. Okay, here for contact behavior we need to define the tangential behavior, that is the frictional behavior, and here we will need to define the coefficient of friction. Let's use some suitable values. Okay, I am using some ad hoc value to build up the model, and also you need to define the normal behavior, like how it behave when we apply some pressure, how the pressure will transfer. So by default we'll use the hard contact. That means that the pressure what is applied on the master surface, that is in the pile surface, will be equally transferred to the slab surface without any difference. So same pressure will be exerted. And for details please follow any standard textbook on contact mechanics, or follow Abaqus manual for more details on this. Okay, and this is important, allow separation after contact. Okay, this says that, I mean what is written, that is what it says, that it will allow the separation when there is a tensile state of stress, when the tensile loading, there will be no contact, right? The contact should open up, so this option allows you to do that. So contact property is defined, and now we'll define our interaction, surface to surface interaction. And the first interaction between pile bottom and soil bottom. and we will consider small sliding, and we can use these options, but those are not very much necessary. Okay, and another thing is this, and here we'll define interaction between the sides, soil sides. Okay, and these are few options you can take on, take off, and see what is the difference. So this is the bottom, and this is the sides. Okay, interaction is done. Now let's apply few loads. First load should be, we want to fix the bottom of the soil. So soil bottom, and we want to actually pin, because it is 3D, we have 3 transitional degree of freedoms only, so we will pin, and on the sides we'll like to restrain the horizontal movement, right? So we have this sides, and we have this u1 u2, like displacement in x and y direction is restrained. Now we want to also apply some load. Okay, no, before load we have to do something more. Is when we'll simulate the self weight of the soil, at that point there will be no pile, I mean there is no contact, right? In the geostatic step there is no contact will initiate in the next step. So the soil here will be unstable if we do not apply any boundary condition. So we need to apply laterally restrain that boundary, and this is okay, but we'll deactivate it when once the contact appears, right? Okay, and on the top finally we'll apply load, right? Apply load on top of the pile, and we'll do that on pile top, and let's apply some reasonable, and it should be vertically downward. Okay, also one thing I observed that we should also make the pile restrain, some sort of restraint during this contact initiation stage, because during contact initiation the soil try to transfer the stress to pile. If there is no boundary condition in the pile, then it causes some, I've seen that it causes some numerical convergence. I'll fix it here, and then when we are applying load we'll modify this value. I mean we create a boundary condition with 0 displacement in vertical direction, and then we apply vertically downward 0.1 meter displacement. Okay, and another thing is left is about the self weight of the soil. To do that we'll, and this self weight should be applied in the geostatic step. Okay, it is self weight, this is gravity, mechanical, and the component here in it is in the direction 3, and we can use some coefficient for g, right? Okay, you may question that why 9.81. okay, I'm just thinking that meter per second square for g, and again regarding all the material properties we should follow some standard paper to get some reasonable result. Okay, So we have this load self weight on. It is not for the entire model. Let's consider it only for the soil. Okay, this will make more sense. Okay, so now I like to mesh from the parts individually. So to do that we need some seed in the 0.02. Okay, mesh part. Okay, let's see the mesh control. Okay, with this the mesh should look nicer. Okay, it's a nicer mesh. And but it takes too many elements. Okay, sounds okay for soil. Okay, we need to use some local refinement. Here also you can use the same technique. Okay, you can always use some more partitioning or more local, using local seeds we can generate better elements. Okay, see, this is how you can see the details of the elements. Okay, this reduced integration, 8 node 3D elements, break element. All right, so now we have mesh and load. Okay, let's create a job. This is my old trial, so this is my new job. Okay, okay, okay. Let me tell you the details. This is the log. Here you can see the big overviews, and you will see the warning message if anything is there. But don't worry about the warning message, because the numerical stuff with non-linearity, so there will definitely some warning message there. And this is the data file, or you will see .dat file is for data file. If you go to the working directory where the file is stored, and this is a message file where it shows writes about details of the analysis, the residuals, all these details. And this is the status file, that is what is you are observing it right here. Okay, all right, looks like the simulation is running well. Okay, and it is done. Let us have a look at the result. Okay, we'll not see this result. This is the new result. Okay, let's rotate. Okay. We'll go check step by step. All right, this is the beginning of analysis. There is no stress, and this is the end of the geostatic let's only keep the soil part. And let's see the state of stress here. On top the stress is okay, we should see the S33 first. On top it is negligible, almost zero. In the bottom, because of the self weight, we have, because I have considered a density of 10 to the minus 2, and that it is multiplied by the G value around 9.8, so the value is seems to be able to be correct. And because of the Poisson's effect, we are seeing these stresses in the horizontal directions also. Okay, now we can use this cut option to see more details. Okay, after geostatic there is contact, so we have this pile is introduced here, and because of the introduction of the pile there will be some small changes in the state of stress. Then we have started applying load here, right? In the next step is load application, and when you start applying load, of course there will be state of stress will be different, right? And if we remove the pile the time being, and we can see, okay, the blue is compression, right? Negative means compression, so we have huge compressive stress here, and tensile, because when it is compressing the bottom, and there, and of course there will be tension in the nearby region. So this area is the highly concentrated stress you can see, and because of this we should see some plasticity over there. Okay, the plasticity is not great till now, but yeah, there is some plasticity. The plastic strain is really significant, 0.1 is significant. But to model this localized plastic stress plasticity, we should use more refined region around here, and in that way we can correctly simulate the stress localization and plasticity calculation. Okay, but I am not going to do that. This could be a task for your project. So anyway, so now so far we have could model the problem as two different parts, pile and soil. We have created three steps, analysis steps: geostatic, contact initiations, and load application. And we have defined self weight for the soil and some boundary conditions which suitable for the problem, and simulated the problem. Okay, and also mesh the problem, discretized using 3D brick element, reduced integration brick element, and we have some result. And of course we should use suitable material parameter and geometric dimensions from some literature, and simulate the problem, and try to, we can, if the model works well, then we can compare the result with experimental observation. That should be the overall goal. Thank you, that's all. Hope this helps.